robotics, IoT, and cloud computing. For this session, Mr. Ugo Chukwu Godson is with us, who will be taking the lecture on embedded system and IoT devices for smart farming. So please give me some time to introduce him. Mr. Godson is an electronics engineer by profession and holds his graduation in physics from Federal University of Agriculture, Nigeria. And he is also founder and CEO of Ugovation Limited, which is Nigeria-based company, and actually deals with designing and developing power inverter for domestic and industrial uses, embedded system for school and organizations, printed circuit boards, Android mobile application, problem-based electronic devices, as well as IoT devices. He has developed many devices or system in the field of Internet of Things. Out of them, he got patent acquisition of one device, which is named as ringer snout, and it is basically meant for detecting gas leakage or smoke leakage or carbon monoxide leakage with audible alarm, visible warning indicator, as well as some call and text feature incorporated in that device. So with this significant real life experience, I would like to welcome and invite Mr. Godson to take this session on embedded system and IoT devices for smart farming. So over to you, Mr. Godson.
Okay, good day, everyone. First, I would like to appreciate the organizers, especially Dr. Pretty, for the opportunity that they granted me to be part of this section. It came as a surprise, I must say, but I'm happy to be here to share my experience in electronics engineering and IoT devices. So with that, we can kickstart. So I would like to share my screen now.
Yeah, please.
Okay. Okay. So can you see the screen?
Yeah, it is visible.
Okay. Yes. So the topic we're looking at today is embedded system and IoT devices for smart farming. Okay. To kickstart that, there are three terms in the topic, as we already know. Number one is embedded systems. Number two is IoT devices. And the third one is smart farming. So we will take them one after the other so that we can understand.
Mr. Godson, can you make it a slideshow? It will be much more better visibility in that case.
Okay. Okay. Is it better?
Yeah, perfectly fine.
Okay. So, like I mentioned, there are three terms in the topic, which are embedded systems, IoT devices, and the third one is smart farming. So, like I said, we'll be taking them one after the other so that we can understand them better and how we can use embedded systems and IoT devices in smart farming. So to start with, we will need to understand what an embedded system is. So like I defined here, an embedded system is an electronic or electromechanical system designed to perform a specific function, and it's a combination of both hardware and software. The software can also be described as firmware. Okay, so embedded systems are managed by microcontrollers or digital signal processors, that's DSP, application-specific ICs, field programmable gate arrays, and as well as gate arrays. Okay, embedded systems programming instruction refers to as firmware are stored in read-only memory or flash memory chips running with limited computer hardware resources. Embedded systems connect with the outside world through peripherals linking input and output devices. So as we go on, we'll see all these peripherals and how they work together with the IoT devices. Okay, so here is an overview of what an embedded system really is. So almost everything we use on daily basis are embedded systems, ranging from manufacturing equipment, domestic appliances, audiovisual equipment, gaming console, telecom equipment, medical devices, cars and vehicles, motion sensors, even our mobile phones are examples of embedded systems. Okay, so and here is how an embedded system really is. At the center of it, or we can say at the brain of it, is a CPU, that's the central processing unit. And for the CPU to function or to perform the function that is meant to perform, it will have to have a software running in it. In our own case, we call it code. So it has to be coded for it to perform any function. So connected to the CPU is the field programmable gate arrays, as well as application specific ICs. And the CPU also has a memory where the software is stored, and it has digital to analog conversion, which works with the actuators. Well, as we go on, we'll see how all that is being connected. And it also has an analog to digital conversion, which is connected to the sensors. It also has a user interface, which can be a screen or um, indicators. And it also has a diagnostic port, which can be used to check if there are errors in the functioning of code that are written into the CPU. And it also has an auxiliary system, which can be the power, the cooling, and the rest of them. So the actuators and sensors, of course, must have power source, which can act as electromechanical backup uh, for safety. Okay, and they interact with the external environment. That is, the sensors and the actuators interact with the external environment. So let's move on. This is just an overview of what an embedded system really is. Okay, so to make it a bit simpler for everyone to understand, so we have an embedded system here, and there are four major parts of it. The first one is the microcontroller or the microcomputer, which is actually the more like the brain of the system, and I call it the control unit. It's the one that performs all the coordinations and controls of the whole unit. Then we have the software or the firmware, which I term as the code. Without the code, the control unit cannot perform its function. Okay, the code has to be put into this control unit for it to perform its functions. So, and the third one, we have the sensors and actuators. These are the ones that interact with the external environment. The sensors collect data from the external environment, put it into the control unit, and decision is made, and actuators are being instructed to carry out instruction based on what is written in the code. So I call the sensors and actuators the input and output devices. And of course, we cannot have a system working without a power source. So the system can either be powered by a battery or solar panel or both. So without the power, nothing functions. So this is just a basic way by which we can understand how an embedded system is made. So moving on. So now we are moving to microcontrollers and microcomputers. So what is a microcontroller? A microcontroller is a small computer on a single integrated and architecture circuit. Microcontrollers have an execution time in the order of microseconds. Okay. Types of microcontrollers. We have the AVR microcontrollers. We have the AMR, ARM microcontrollers. We have the PIC microcontrollers. We have the 8051 microcontrollers, as well as the MCP microcontrollers. Okay, so all these are types of microcontrollers, but we're narrowing down this lecture to AVR microcontrollers as well as the ESP32, which we'll see in the other slide. Okay, so sorry, please. Okay, so moving on. These are the various types of microcontroller modules that we have. These ones are made by a company called Arduino. Although we have other uh, companies that make the same kind of board with the same functionality, but these particular ones are made by a company called Arduino. So these are the various ones that they've made that we use in embedded system design. So here we have the Arduino Leonardo, that's the name they gave it. Here we have the Arduino Uno, which is the most common one used by us all hobbyists in embedded systems. We have the Arduino Mini, we have the Arduino, and we have the Arduino Mega, as well as the Arduino Elipad. So these are just the various types of Arduino that are in the market, are being made by. There are other ones too that are made by them, but of course these are the most common ones. So the choice of the microcontroller to be used depends on the user and what he or she wants to achieve. Okay, so move on to another type of microcontroller, and these are called ESP32 microcontroller. These ones are made by a Chinese company called Expressive Systems. So they're the one that made these microcontroller boards. And these are actually the best, according to me, the best microcontrollers, best candidates for IoT devices. Why? Because they have all the features required for IoT connectivity. They have Wi-Fi, Bluetooth, and several other wonderful features that are good for IoT applications. Okay, so moving on, we also have the Raspberry Pi and Raspberry Pi boards. So I don't make use of this because I work basically with Arduino boards or Arduino IDE. So, but these are actually microcomputers that are much more advanced than basic microcontroller boards. These are basically microcomputers, and they can actually run uh, an OS, an operating system. So they have much more features than the um, microcontrollers that we've seen that I've shown in previous slides. Okay, so we will not be focusing on Raspberry boards because I don't make use of them in my own designs. So to understand how a microcontroller works, so we're looking at the basic structure of the microcontroller. At the center of it is the CPU, which you can see. That's the central processing unit. That's where the decision is being made. That's the control unit, actually. Then we have the RAM, that's the random access memory, where the code that the CPU runs on is being stored. Okay, we have the clock, we have the ADC, which is the analog to digital converter. We have the ROM, that's the read-only memory. We have the IO, that's input and output pins on the microcontroller, and also we have the DAC, which is the digital to analog converter. So this is the basic structure of a microcontroller. Without all this, microcontroller cannot function. They are all present in every single microcontroller that is being used for embedded systems. Okay, so moving on. This is the basic structure of a Raspberry Pi board. At the center is the processor, which is called BCM2835 system on chip processor, and it has Ethernet connector, it has USB port, it has power supply, it has GPIO ports, which can be used to connect external devices. It has the camera, it has the SD card slots, it has the display outputs or display ports, and also the HDMI port. So this is the basic structure of Raspberry Pi board. So we'll move on to the next one. So here we have an Arduino Mega board. I chose this one specifically um, to illustrate the what I've explained initially regarding the structure of a microcontroller. So looking at it, at the center of it, we have the microcontroller itself, which is the Atmega 2560 microcontroller. That's the one that is performing functions. So every other thing around this one here, the IC that is used to program the microcontroller. That when you connect it to the PC, it's used to program the microcontroller. Then around it, the black ports are just input and output ports, as well as power ports that can be used to power the microcontroller. And here we have the USB to computer ports that can be used to when you connect it to the computer sees it as an external drive, and you can run your code on it for it to start working. So every other component and device around in there is just supporting the whole system to make it work the way it should work. Okay. So moving on, we have the ESP32 pinout diagram. So, like I mentioned, this is the best candidate for IoT devices. And as you can see, it has a lot of input and output ports, pins. So here is actually the main ESP32 itself. And the programmer here, the power regulator or the voltage regulator, the USB ports to be connected that can be used to connect to the PC, and the GPIO pins, that general purpose input and output pins. Okay, it has all the required connection protocols, which include the IIC, the SPI, and the rest of them. It also has touch pins that respond to human touch. So it has so many features, including Wi-Fi, Bluetooth, and the rest of them. So this is the best candidate for IoT devices. Okay, moving on, we have here the Raspberry Pi pinout diagram. As you can see, we have the header pins, the system on chip, that's the CPU itself, the USB to Ethernet controller, the USB ports, the Ethernet, and the HDMI, the power, the indicators, the DSI, the Wi-Fi and Bluetooth, and the rest of them. So this is just the basic pinout diagram for Raspberry Pi boards. And like I mentioned earlier, I don't make use of this, so I don't have much information regarding it. We're not going to focus on this for this lecture. Okay, now we are moving on to, we have now taken care of the hardware parts, which is the microcontroller part. So like I mentioned earlier, for it to work, it has to have a software running in it. So we're going to be looking at what the software is and the types of software that we can use for programming the microcontroller. So I define here embedded software. So what is an embedded software? Embedded software is a piece of software that is embedded in hardware or non-PC devices. It is written specifically for the particular hardware that it runs on and usually has processing and memory constraints because of the device's limited computing capabilities. So embedded software is used for overall operation of the system. Like I mentioned earlier, without it, the system cannot function. Okay. Now, a little different between the software and firmware. Firmware is a special type of embedded software that is written on non-volatile memory, such as the ROM or the EEPROM. Okay, that's a read-only memory and erasable programmable read-only memory. That's the meaning of EEPROM, which cannot easily be modified. Hence, the name FEM, and it's usually primarily for running or booting of the device. We can relate this to the operating system of our mobile devices. We have Android and the iOS as a common. So is the OS in this case that's called the firmware for the embedded systems or the CPUs for the embedded systems. Okay, so moving on. So we have different programming softwares that we can use to program the embedded or the microcontrollers. Sorry. The first one, which is the one I make use of, is the Arduino IDE. That's Arduino Integrated Development Environment. Is the most common one. It's open source and it was developed by a company called Arduino. So it has so many users and then a lot of people have contributed to it, and which makes it easier for other people to use it to do their own development. So it can be used to program AVR microcontrollers, Arduino modules, as well as ESP32 modules. Okay. We also have the platform IoT. This one is an extension in VS Code. Okay, if you're familiar with VS Code, we have this extension there, and we can use this one to also program AVR microcontrollers, Arduino modules, as well as ESP32. So the choice of using either of these two depends on the user. They have similar features and also some features that are different from each other. So, and the third one is the ESP IoT Development Framework, or we can call it ESP. So this one was developed by Expressive Systems, which is a company that developed or that is producing ESP32 boards. So they developed this software for programming ESP32 microcontroller. Okay, so these are the most common ones. There are several other ones. You don't have to go into all this, but these are the most common ones. All right. So this is an Arduino IDE user interface. This is what it looks like when you are programming Arduino IDE. So you open it on your PC and you write the program the way you want to write it and what you want it to do and how you want it to perform. So after writing the program, you connect your microcontroller to your computer. Your computer sees it as an external device, and you select the appropriate port, select the appropriate module that you want to program, and then run the program. So if there's any error in the code, the software will tell you and to flag the error so you can make corrections. And it also has here the serial ports or the serial monitor, which you can use to do debugging. I used to check if the code is working as you want it to work. So this is the software that I use for my own development. Okay. Then moving on, we have the sensors. Okay. We'll discuss the microcontroller, we'll discuss the software. Now we're moving to the sensors. Now, what are sensors? A sensor is an electrical instrument that monitors and measures physical aspects of an environment and sends an electrical signal to a control control module, which can be the microcontroller or the microcomputer. And sensors turn physical inputs into electrical signals that are outputs to the control module. So there are many sensors that can be used to collect data from the external environment. And these sensors, what they do is when they collect this data, they change it to electrical signals, which they supply to the control unit, which is the microcontroller. And the microcontroller uses it to take decision based on the instruction that we put in code. Okay. Now, examples of such sensors include the PIR, that's partial infrared motion sensor, the temperature sensor, the moisture sensor, and say soil moisture sensor, soil pH sensor, humidity sensor, soil nutrient sensor, anemometer to measure wind speed, as well as rain sensor. There are so many of them, but I just pick this one because they are related to agriculture. Okay, there are many of them out there that we can also use. We also have other ones that are used in agriculture also, but I just pick this few to illustrate what a sensor really is. Now, we also have the actuators. Now, what are actuators? Actuators are electrical instruments that take electrical signals from control modules and turn them into physical outputs. So they perform a wide range of functions from turning rotors and valves to virtually anything else. So actuators are actually output devices, okay? They are used to perform functions. For example, if you have a robot that is meant to perform a particular function, then the actuators there will be the motors that make it move, the servo motors that make it turn in different directions or do other perform. So those are actuators. They're also directly connected to the control unit. So when the sensors get the data, the control unit takes the decision and sends a message or signal to the actuators to carry out function that is being put in the code. Okay, examples of such actuators include servo motors, electric motors, relays, solenoid valve, stepper motors. Okay, so we'll be seeing some pictures of them in the next slides. Okay, so these are some sensors that we have. I just picked a few of them. Here we have the BMP 280. So this is actually temperature, pressure, and humidity sensor, 3-in-1. It can sense the three parameters at the same time. And it connects to the microcontroller using the IIC protocol. Okay, so that's how it communicates with the microcontroller or the control unit. Here we have the PIR motion sensor, which senses movement or motion of humans, especially, or any other animal that emits infrared from their body, or can say warm-blooded animals to be precise. So next to it, we have the soil moisture sensor that can be used to detect the amount of moisture that is present in the soil. Okay, and going down, we have the soil NPK sensor. We can simply call it the soil nutrient sensor. This can be placed on the farm and buried into the soil to detect the NPK content, that's nitrogen, phosphorus, and potassium content of the soil. It's connected to the microcontroller as usual. Whatever instruction is put in the code is what will be carried out by the system. So next to it, we have the anemometer. So this one measures wind speed and possibly wind speed specifically. This can also be used in farm. It's used in farm, of course, to measure the speed of wind in that particular location. Okay. Then next to it, we have the rain sensor. So this can be used to measure if rain is falling or not. And it's also connected to the can be connected to the microcontroller as usual, just like every sensor I've mentioned. Like I said before, there are many of them that can even be used in smart agriculture. I just picked a few so that we don't spend too much time on that. Okay. Then we have the actuators. Here, the first one, here we have the servo motor. The servo motor is a kind of motor, a special kind of motor that is used to perform some specific functions. It's mostly found in robots. Okay, if the robot is meant to maybe twist or turn or whatever, it's servo motors that are used majorly for that purpose because it has some high amount of torque that can be used to turn objects around. So next to it is the electric motor. This does the spinning, can be used to perform spinning or rotational movement if the need be. Okay, it's mostly found. Well, we've seen fans and yeah, let's just say fans. So what is in the fan is an electric motor. It can be either AC or DC. Then next to it is the solenoid valve. So this can be used to control the flow of liquid or gas. It can be used to control the flow of liquid or gas. Okay. So it is electrically controlled. We can apply when the two pins that are there, when you apply the required voltage for the device, it's whether open or close the valve so as to allow flow of liquid or gas or stop it. Okay, so that's a function of it. So next to it, down here, we have the stepper motor. This is basically a type of electrical motor also, and it's it has a much higher torque because it moves in steps and can be used to drive uh, high power devices. So examples are the printers we have that print on paper, the 3D printers, the CNC machines. So these are the devices that use uh, stepper motors. Okay. Then next to it, we have the relay. The relay is actually an electromagnetic switch that can be used to switch on or off other devices external. Okay. So these are the few actuators that can be used in embedded systems. Okay, there are so many of them also, as I mentioned before. So moving on, we have the power system. So this is just a basic illustration of how an embedded system can be powered. So there's other methods also, but I just pick this one so as to give the right illustration. So here we have the solar panel. On the solar panel is one that, of course, we know what the solar panel does. It converts the energy from the sunlight to electrical energy to perform work. Okay, connected to it is this is a boost converter or a charger, so to say, that takes in the power from the panel and converts it to the appropriate voltage to charge the battery that we have there. So a lot of devices that we are using today, including our mobile devices, use lithium-ion batteries. And this is actually the battery that I use for my own embedded system development also, because it has a lot of advantages. Okay. So the panel charges the battery via the charge controller or the boost converter or buck converter, whichever one it is. And it's also connected to the Arduino board. This is an Arduino board, just an illustration like I mentioned earlier. So the Arduino board takes power from the battery. So this board runs on 5 volts, or it can also take more than 5 volts from the input pin. But the function of this boost converter that is here is to convert whatever voltage is coming from the battery to 5 volts to run the board. So this is the basic illustration of how an embedded system, yes, embedded system can be powered. So like I mentioned earlier, the part of the embedded system is the microcontroller. So as soon as the microcontroller is powered, Some other ones can be powered also, though some of the actuators and the sensors can be powered externally by other sources. But a lot of them, especially the sensors, can also be powered using the power grid that is supplying the controller itself. Okay, so let's move. So now moving on to the second term in the topic that we're dealing with, IoT devices. So what is an IoT device? Let's start with what IoT means. And IoT means Internet of Things. It's not new to us. It has been around for a very long time now. So Internet of Things is a system of interrelated or interconnected computing devices, mechanical and digital machines. So before the invention of IoT, what we have basically is our computers connecting to the internet. Okay, so that's why we have the internet. But in this case, we have Internet of Things. So things means our computers, our embedded systems, our machines, and everything can be connected together. So that's what IoT basically means. Now, what are IoT devices? IoT devices are devices that connect wirelessly to a network and have the ability to transmit and receive data. Okay, so that is very, very simple. They connect wirelessly to a network. The network can either be a local one or over the internet, and they can transmit and receive data. Okay, mobile phone is an example of an IoT device. ESP32 that I mentioned earlier is an example of IoT device, and other devices also. Even our computer is an IoT device. Now, IoT involves extending internet connectivity beyond standard devices such as desktop, laptops, smartphones, and tablets to any range of traditionally non-internet enabled physical devices and everyday objects. So this is self-explanatory. IoT can be extended to all this, and that's why it is being applied in smart farming uh, these days, and even in industries. IoT is applied now. It's a very common technology. So moving on, we have these different types of IoT devices. Number one here is a mobile phone, which almost everybody has. And following that is the PC, a desktop computer. It can be laptop, it can be uh, tablet or whatever. So this is also an example of an IoT device that can connect to the internet. Then the third one, as I mentioned earlier, ESP32 board. This one can connect to the internet also because it has Wi-Fi capabilities. Also has Bluetooth and several other features. So the fourth one here is a drone. We are all conversant with what drone is nowadays. It's commonly used for taking pictures and pictures and for exploring um, some terrains. So it's a common machine that is being used today. Then following that, we have a robotic arm. So in our industries now, many industries are being automated. Many production processes are being automated, and most of them make use of robotic arms to perform these automations. So these robotic arms can also connect to the internet. It can be controlled either locally or from anywhere in the world. Okay. So the next one is smart TVs. This one also connects to the internet. Then the next one are robots. So I just picked this picture because these are the ones that are being used on the farm to either to plant or to do some other things. So these are robots that are in the farm. So they can also connect to the internet. As you can see, there's no human being close by. So they are just performing their functions based on the instruction that they are being. Okay, they can also be controlled from anywhere in the world. Okay, so these are just the few types of IoT devices, the most common ones that we know today. So now moving on, what exactly is smart farming? Okay, smart farming refers to the managing farms using technologies like IoT, robotics, drones, and AI to increase the quality and quantity of products while optimizing the human requirement production. So smart farming is basically making farming processes much more easier by using state-of-the-art technologies like we mentioned the IoT, robotics, drones, and AI. Okay, that is what smart farming is basically. So this picture here is just an illustration of what smart farming is. Okay. The first one is the sensing technology. We have treated sensors above. We have looked at what they are and what they are being used for. So the first one is sensing technologies. We need to sense what is in the farm, or the location, temperature, pressure, wind, and soil, moisture, and the rest of them. So that's the first one. Then the second one is software applications. Okay, software applications can be either mobile software or web-based software. Okay, then the third one is the communication systems, e.g., cellular. So for you to be able to connect to the internet, you need a communication system. Um, the one that is mostly used is cellular communication, which can either be GSM, GPRS, um, Edge, or 4G, or whichever one is available to be able to connect to the internet. You need the communications system. Then the fourth one is the telematics or positioning technologies. Here, of course, for most IoT devices that are placed on the farm, they all have positioning technologies. And this can be GPS module that tells the exact position of the device, okay, and where it is on the farm, which farm it is communicating from, okay. Then the fifth one is the hardware and software system. Of course, like we've treated, we need the hardware, which is the embedded system, as well as the software that is the embedded system. And the sixth one is the data analytics solution. So data is being collected by the sensors, uploaded to wherever, either the cloud or locally to the collection center. And this data must be analyzed to be able to, for it to be able to make sense, or for the farmer to be able to use it to do the needful. Okay, so this is basically what smart farming is. All right, so let's move on. Now, the technologies that are available for smart farming include sensors, like we mentioned before. We have the soil sensor, water sensor, rain sensor, light sensor, humidity sensor, temperature sensor, wind speed sensor, and several of them. So the sensor must be there to get the fire data from the farm. Then the software, specialized software solutions that target specific farm types or applications. And this includes mobile application as well as web applications. Okay. Then connectivity, we can either use cellular connectivity to connect to the internet or connect between the devices, maybe that are placed on several locations in the farm. Or we can use another technology called long range. That's the full meaning of LoRa. Long range. It's also relatively new and can be used to transmit data for a very long distance. It does not depend on the cellular connectivity that we use. he works on a phone and can transmit for several kilometers. Okay. But of course, you can't use it to transmit large amount of data, just few kilobytes or bytes of data. So the third one here is the radio frequency. This is also another common uh, connectivity, another thing that can be used to connect between devices on the farm. Okay. Then moving on, we have the location. Of course, you must know the location of the farm and or the exact location of the system that we are dealing with at a point in time. So the location can either be the GPS or the satellite. Of course, the GPS works with satellites to be able to get the exact position of the particular uh, system that we're dealing with. Okay. Then we have the robotics. Now, robotics include autonomous tractors, processing facilities, surveillance robots, and the rest. So, robotics is also a technology available for smart farming. Like in the um, picture I showed earlier, the the robots that they showed there used to uh, maybe plant or survey the farm. So that's also there. Then data analytics. So this is a standalone analytics solution, data pipelines for downstream solutions and the rest. Okay. So these are basic technologies that are available for smart farming. Okay. Now, like I said, when farmers are armed with these technologies, they can monitor field conditions and make strategic decisions for the whole farm or a single plant without even needing to step foot in the farm. So most of these IoT devices, which depend on embedded system, can connect to the internet. So wherever the farmer is in the world, anywhere at all, farmer can monitor what is going on in the farm. We can even have robots that can take pictures or take videos and upload to the cloud. Or drones can also be used to do that. Okay? So the farmer doesn't even need to step foot in the farm to be able to do all this. Can to to monitor his or her farm. Okay, so um, so petition. Okay, sorry. So IoT based smart farming using embedded systems. IoT based smart farming using embedded systems. So this is actually combining everything that we're talking about since when we started. So the core of IoT-based smart farming is data that the farmer can draw from things and transmit over internet. To optimize the farming process, IoT devices installed on the farm collect and process data in a repetitive cycle that enables farmers to react quickly to emerging issues and changes in ambient conditions. So this is self-explanatory. So the main purpose of using IoT devices on the farm is to collect data, transmit it to the internet, either store it on the database or live transmission, and for the farmer to be able to make decisions based on what information or data is being collected on the farm. Okay. Now, smart farming follows the cycles like this. The first one here is the observation. So the observation is being done by sensors that we discussed earlier. Sensors record observational data from crops, livestock, soil, or atmosphere. So that is the first uh, thing that we done, collection of data or observation. Then diagnostics. The sensor values are fed to cloud-hosted IoT platform. Predefined decision rules with predefined decision rules and models that ascertain the condition of the examined object and identify any deficiencies or needs. Okay, so this data must be transmitted to cloud server or can be also transmitted live to the farmer. But the best way is to store the data on cloud server so they can access anytime and anywhere. Okay. So such databases include Firebase, ThinkSpeak, Blank, MQTT databases. There are many of such databases that can be used to store data that is being collected on the farm. Okay. Then the third one is decision. After issues are reviewed, the user or the machine learning driven components of IoT platform determine whether the location specific treatment is necessary and if so, which. So this decision can either be done by the farmer or user or can be done by an AI driven uh, platform or machine learning driven component. So when the decision is taken, then the next thing that will be done is action. So for example, if a soil moisture sensor is being installed on the farm and the sensor captures the data, which is the observation, diagnoses the data that is sent into the database, and decision is being taken, meaning that if the uh, level is lower than a certain amount or certain percentage, then action is being taken. Such an action can be either to turn on the machine to irrigate the farm or whatever. So that's just an example of such cycle. So the cycle repeats itself. Okay, observation, diagnostic, decision, and action repeated like that. So moving on. So I present here an example of an IoT-based smart farming device that we developed for a client. So here it's pictured undergoing a test on the table. It hasn't been deployed on the farm at this level yet. So here we have a sample of soil, and in there are two sensors. The first one is the soil moisture sensor, and the second one is the soil temperature sensor. So those are the two sensors that the device uses. So this device is IoT enabled, meaning that it connects to the internet via Wi-Fi and is being powered by ESP32. We'll see that in the next slide. So it connects to the internet and stores the data, these two data, which is the soil moisture sensor and soil temperature sensor on the cloud. So the cloud server that this one uses, this particular one is Firebase. So which is very easy to use by developers like us. So like I mentioned, it's an automatic irrigation system. So meaning that it monitors the level of moisture in the soil, and based on the level of moisture, the device takes action on its own, either to switch on the pumping machine to irrigate the farm or turn it off when the moisture level is high enough. And picture down is a mobile application that we developed for this device. So as you can see the percentage of the moisture in this soil that is being tested is showing 19%, and the temperature is showing 27.06. So this app, like we have seen, can be the user can have it from anywhere and can access the the device. And down there in the app, you can also turn on the pumping machine manually or turn it off. So it depends on what the user wants. So this is basically a kind of system, a kind of an example of IoT-based smart farming device based on embedded systems. So we developed this one for a client. So take a closer look at the device itself. So you can see it has a screen uh, that displays the date, the time, the moisture level, the temperature of the soil, the pump state, either on or off, and the pump mode, the device mode, either manual or automatic. So when it's a manual mode, the pump can be switched on or off using this switch, this green switch on the device or from the mobile application. And when it's on automatic mode, the pump is being turned on or turned off based on the percentage of moisture in the soil. So it was still undergoing testing as at this stage. Okay, so this is, like I said, is an example of an IoT-based smart farming device, and it's called an automatic irrigation system. So to illustrate how those components are being connected, so I show here a picture of the internal structure of the device. So you can see that at the center, we have the microcontroller, which the one we use is the ESP32. Like I said, it's the one that I make use of mostly for IoT-enabled devices. We can see here the battery, which is the lithium-ion battery. We can see here the boost converter. You can see here an actuator, which is the relay, which is used to switch the pump on or off based on the action that the user. We can also see here, this is the back of the screen. Okay, and you can see wires and all that. This is the amplifier for the soil moisture sensor. So this is just the internal part, just to illustrate how these devices are connected together to perform the function. So the software that this ESP32 is using to run the whole system was developed by us and was programmed into the device to perform the function that it performs. So this is an example of a smart farming device, an automatic irrigation system. So we also developed, though not for a client, we just developed this for it's a robot, a surveillance robot actually, and it's a prototype robot that we developed, and we are working on developing better versions of it. So as we saw in one of the slides, robots can be deployed on the farm, either for surveillance purpose or for other purposes. So this is an example of such a robot. This one is a surveillance robot. So this one, as it is being controlled from a mobile app that we're also developing. We are developing an IoT system. So this robot is being controlled from the app. So if such a robot is being put on the farm, it can be controlled from either a mobile app to web app from anywhere in the world. You can take pictures, you can uh, do assessments, maybe of fruits, of leaves, and all that, and upload the data on the database. Okay, so these are just the rear view of the microcontroller. I mean, sorry, the robots that we developed. Sorry about that. So now moving to the ending part of the lecture. So we have importance of IoT-based smart farming. Number one importance is precision farming. And what is precision farming? Precision farming, or we can also call it precision agriculture, is an umbrella concept for IoT-based approaches that make farming more controlled and accurate. In simple words, plants and cattle get precisely the treatment they need with accuracy. So this is one importance of IoT-based smart farming. So precision farming, it helps farmers to get an accurate treatment for their plants and livestock. By precisely measuring variations within a field, farmers can boost the effectiveness of pesticides and fertilizers or use them selectively. Okay, so this is self-explanatory. Then precision livestock farming also is also an importance of smart farming. And what is that? Precision farming technique enables farmers to better monitor the needs of individual animals and to adjust their nutrition accordingly, thereby preventing diseases and enhancing herd health. Okay. Large farm owners can use wireless IoT applications to monitor nutrition, well-being, and health of their cattle or other livestock. With this information, they can identify sick animals so that they can be separated from the herd to prevent the spread of disease. Okay, these are two major importance of um, IoT-based smart farming. And the other one that we have there is IoT-driven smart greenhouses. IoT-driven smart greenhouses, and these are, can say, IoT-driven smart greenhouses can intelligently monitor as well as control the climate, eliminating the need for manual intervention. Various sensors are deployed to measure the environmental parameters according to the specific requirements of the crop. That data is stored in a cloud-based platform for further processing, control, and control with minimal intervention. So, like I illustrated earlier, the device that we built for a client is automatic irrigation system, which monitors the temperature of the soil as well as the moisture content of the soil. So, and the device takes decision on its own based on the setting of the user. So, either to switch on the pumping machine or turn it off as at when due. Then the fourth importance is agricultural drones. Agriculture is one of the major verticals to incorporate both ground-based and aerial drones for crop health assessment, irrigation, crop monitoring, crop spraying, planting, soil and field analysis, and other spheres. So drones are used basically for a whole lot of things on the farm. Okay. The data drones gather provide farmers with insights into a whole metrics, plant health indices, plant counting and yield prediction, plant height measurement, canopy cover mapping, field water pond mapping, scouting reports, stockpile measuring, chlorophyll measurement, drainage mapping, weed pressure mapping, and so on. So these are the major four important of uh, IoT-based smart farming, of course, using embedded systems. So with this, that marks the end of my own section. Thank you very much, everyone, for listening. I really appreciate the uh, organizers of this section and for allowing me to be part of it. Thank you. So I will now take questions and comments.
Yeah, thank you very much, Mr. Godse. Right now, we do not have any question from the participant side. I just wanted to know, you have shown in one slide that is farm survey robot, right?
Please come again.
Yeah, farm survey robot, that
Okay.
IoT device. So
Yes.
what are the challenges in front of that type of IoT devices, because it is very much small and portable size, and
Yes.
while running it into the field, it will get some uneven paths. So is it okay to such kind of devices? It means that operation is very much okay in that case?
Okay. Like I mentioned, it's just a prototype and that we are working on. That particular prototype is not meant for farms, actually. I just put it in this presentation just for illustration purpose. So for the robots that are fit for farm, Of course, they'll be big enough to be able to access any terrain and also be equipped with the right movement, like call it the tires and all that can access any terrain. Okay.
So this size of robot will be not suitable for field?
No, it won't. It's really small. It's small.
And what are the procedure for connecting such kind of IoT devices to the cloud system?
Okay, yes, we can, when we build a bigger one that can access the farm, we can put a little Wi-Fi router into it. Or
yeah, but
sometimes
Wi-Fi has some limitation now. It will work, means Wi-Fi and Bluetooth has some limitation. If we want the complete automation, then we have to go for cloud also.
yes, Wi-Fi that I'm talking about is to connect the device to the cloud. Okay, so the router is just to connect the device to the cloud. So the device itself will have the microcontroller that is running it, and we connect to the cloud using the router. Of course, the router should be maybe 4G enabled for faster connectivity. Okay, so that is just what I would suggest for such application. Okay.
There is one question from audience side. What kind of privacy and data security is required to protect from unlawful exploitation of private information from the farmers?
Okay, so like I mentioned, the one I use basically is Firebase, and Firebase is a cloud service that is being offered by Google. And of course, with that, we are sure of our privacy for the data that has been stored. And the IoT, the cloud, the platform itself has some rules that can be set by the user, such that no other person can access the data except the user. So there is high level of privacy. And when we go for MQTT databases also, we high level security in there. I'm not disputing the fact that there are security issues when it comes to IoT devices, but of course it can be controlled to a higher based on what the farmer is. Yes.
So, Mr. Godson, how you decide if you want to build some IoT device? So, how you decide what will be the feature of your microcontroller or microprocessor? How much RAM it should have, and how much what will be the processor configuration in order to make your device in a workable mode?
Okay. It all depends on what the end user actually wants. Okay, for most applications, the one I mentioned earlier, which is ES32, can actually perform the function. So it doesn't require too much memory. It's the memory that's a RAM is where the code is being stored. And with that, there's enough RAM to accommodate the code that you have to put in the device. So there is no much memory issue. And if there is an issue, you can always expand the memory to accommodate what you really want. But for most farm applications, these devices are capable of taking care of them. And if you decide to go for Raspberry also, they are very much capable.
So does that one microcontroller, like controller or microprocessor like Raspberry Pi, does it work to make a device for IoT device for farm level?
Okay,
or
yes.
we need to increase the configuration?
No, like the robot I showed earlier, it is using two microcontrollers basically. But one is for capturing the video, and the other one is for controlling the robot's movements. Okay, but if we are dealing with if you are working with maybe Raspberry Pi, you can have, like I showed earlier, you can connect your camera to it. You can connect the other peripherals, and we also have something like called input and output expander. If you use that, you can expand the input and output pins to as many as you want. So if you have a lot of things to control at the same time. So the ability for the microcontroller to control everything at the same time depends on the frequency and the architecture of the microcontroller itself. So Raspberry Pi is a very good candidate for those that make use of it. And also for me, yeah, ESP32 is a very good candidate because it's very fast in performing its functions.
Another question from participant side is, do I need to learn how to use Arduino and programming to apply IoT devices into the farm?
It depends on your choice. And like I mentioned, the one I use is Arduino. That is one I like. There are several other platforms that you can use to program your microcontroller. So the choice is yours. Like I mentioned, there are also other microcontrollers such as the 8050 microcontrollers, the PIC. Those ones you can use even C or C++ to program them. So once you have a text editor like VS Code and the rest, you can write your program and upload to the microcontroller and connect other things to it for it to perform its function. So even Arduino is very simple to learn. I learned it on my own, if I may say. So it's very simple to learn and easy to understand. Yeah, it's an open source. It's open source and it has so many people that contribute to it to make it easier for other people to learn. Okay. So.
Yeah, I think I'm done with the question from participant side. So thank you very much, Mr. Godson. I suppose participants who are looking to familiarize with more to the hardware as well as electronic components, how this system works, then I guess your session was a good place for them. So once again, thank you for accepting our invitation and hoping it might be useful for our participant, not all of them, but at least few of them. So thank you very much. So dear participants, we are closing today's session. And yeah, so see you tomorrow for 3 more sessions and good day to you. Thank you for now.
Good day. Good day.